Hello, everyone. Here I share you with some of our recent experiments using deep brain stimulation to modulate the hippocampal network activity and rescue the memory in a mouse model of CDKL5 deficiency disorder. CDKL5 deficiency disorder, or CDD, is caused by the mutation of CDKL5 genes in the X chromosome. The patients have a panel of symptoms, including severe intellectual disability. Several labs have shown the evidence that the CDD model recaptured the core features of the disease, including learning and memory deficits, motor deficits, seizures, and the autistic feature. The initial CDD model with exon 6 deletion shows impairments of contextual and cued field memory. So we use the same model and checked the effect of CDKL5 loss on the hippocampal memory, hippocampal LTP, and the hippocampal inhibition. Then we evaluated the effect of cell DBS on the hippocampal memory, LTP, and the inhibition in this mouse model. This data were published recently. The existing data in CDKL5 model was mostly focused on the male mutant mice, but we were also interested in the female heterozygous mice due to their clinical relevance. So a postdoc, Xuan Hao in the lab, first performed the field conditioning experiments. She trained the mice with toe and foot shock, then tested the hippocampus-dependent contextual field memory and the hippocampus-independent cued field memory. Here I organize the data side by side. Left side is the male mice, and the right side is the female mice. As you can see, compared to the Y-type male and Y-type female mice, the mutant mice has impaired contextual field memory. The male mice also shows impairment of cued field memory. Next, Song used the models of water mice, that's a highly hippocampus-dependent learning and memory task, to evaluate the memory behavior. So this is the training data. So compared to the male Y-type and the female Y-type, the mutant mice need longer time to locate the platform during the training. In the probe test without the platform, the male Y-type mice shows clearly preference to the target quadrant, but not the male mutant mice. As a result, there is the impairment of the reference memory. Female mice shows a similar situation. Y-type prefers the target quadrant, but not the mutant mice. There is the impairment. So this data shows that CDKL5 loss impairs the spatial learning and memory. We know hippocampal syllabic plasticity is a neural substrate of learning and memory. So we checked the LTP in the perforant path to the dentate gyrus pathway in this mouse model. So this pathway conveys large amount of contextual and spatial informations from the cortex to the hippocampus. And importantly, there has never been studied before for the LTP in this pathway. So Swan implanted the stimulation electrode in the medial perforant path and the recording electrode in the dentate gyrus. After recovery, we deliver single pulse to the mouse in the free moving state, which evoked a population spike like this. We measure the pop spike amplitude as indicated by the arrow line. So the experiments were across 7 days from day -1 to day 5. As you can see, the baseline from day -1 to day 0 is stable. Then we use seed burst stimulation to evoke LTP in both wild type and mutant mice. This is male mutant mice. Both groups shows clear LTP for at least 3 days. But compared to wild type, CDKL5 loss causes LTP impairment. Same situation in the female mutant mice. Compared to the wild type female mice, the mutant female mice shows impaired LTP for 2 to 3 days. We know there are different angles to dissect the mechanism underlying LTP loss induced memory and the LTP deficits. But we will interested in the neurocircuitry activity changes, in particular the inhibitory circuitry activity after CDKL5 loss. So we know there are a large number of inhibitory interneurons in the hippocampus. They forms feed-forward and feedback inhibition to modulate the overall network activity. So we hypothesize that CDKL5 loss alters the hippocampal neural circuit activity that mediates the impairment of hippocampal memory and the synaptic plasticity. First, we use a previously established protocol called frequency-dependent inhibition, or FDI, to evaluate the feed-forward inhibition. So the experiment setting is like the LTP. We recorded the pop spike in the performance path to dentate pathway. Basically, 10 pulses were delivered and followed by the another 10 pulses at 1.0 hertz. This protocol was repeated once more, and we use this formula to quantify the FDI index as a representation of the inhibition. Here is the summary data. As you can see, in the male and female mice, compared to the wild type, the FDI index in mutant male and mutant female mice are reduced, which is actually indicate increased frequency, the feed-forward inhibition. So we know there are different category of inhibitory interneurons in the dentate gyrus. We were particularly interested in a group called MAP cells, molecular layer performance path associated cell, which has been previously identified to mediate feed-forward inhibition in the dentate gyrus. So here the performance path projected to the dentate granule cells, and the collaterals activate MAP cells, which project to the same group of dentate granule cells. So another postdoc, T1, performed the following slice experiments. So for this, we use male CDKL5 mutant mice to avoid the mosaic situation in the female heterozygous mice. She performed the dual recording of MAP cells and dentate granule cells. In some recording pairs, injected the current to the MAP cells could induce IPSP in the dentate granule cells, which indicates a direct synaptic connection. So this shows two recording pairs in the same slice. So she first evaluated the spontaneous EPSC in both MAP cells and the dentate granule cells. And she found that the frequency of the SEPSC in MAP cells is increased after CDKL5 loss. But the both frequency and amplitude of SEPSC in dentate granule cells is decreased. So a weaker excitatory synaptic transmission in the dentate granule cells. Then she further evaluated the evoked response by stimulating the performance path and record the input-output curve. The light color shows the data from the wild-type mice. So this shows that the evoked response in the MAP cells is stronger than in the dentate granule cells. The darker data points shows the data from CDKL5 mutant mice. So after CDKL5 loss, the response in the MAP cells is even stronger, and the response in the dentate granule cells is even weaker. This data shows that after CDKL5 loss, the difference between wild type, between MAP cells and the dentate granule cells is further amplified, which shows maybe the dentate granule cells receives more inhibition through the MAP cell mediated feed-forward inhibition. So she directly recorded the SIPSC in the dentate granule cells. And as we expected, she found that the SIPSC frequency is increased after CDKL5 loss. So to this point, the data shows that the loss of CDKL5 skews the excitation inhibition balance of the dentate granule cells towards the inhibition. In other words, there are too much inhibition after CDKL5 loss. If that's the case, we block the inhibition by GABAergic receptor GABAZine directly injected to the dentate granule cells. So then compare the memory. So what Song found is that the fair memory in the hippocampus dependent version in wild type mice compared to saline injected, there is low change because the injected GABAZine dose is very low. But the same dose of GABAZine could enhance the fair memory in mutant mice compared to the saline injected group. Of course, there is low change in the hippocampus independent acute fair memory. So this piece of data shows that blocking GABAergic transmission enhanced the hippocampus dependent memory. So now I have shown you that the CDKL5 loss caused the circuit activity change in the hippocampus. So we consider to use deep brain stimulation to modulate the hippocampal network activity. Actually, we have previously showed that 40-cell DBS could rescue the hippocampal memory in another model of intellectual disability disorders, which is nerve syndrome mice. DBS increase the memory and rescue to the wild type level. So this allows us to hypothesize that 40-cell DBS improves hippocampal memory by modulating the circular activity in the dentate gyrus of CDKL5 mutant mice. So Swan implanted the DBS electrode in the femoral pharynx under the guidance of evoked potential recordings in the dentate gyrus. We implanted the electrode at the age of 6 to 8 weeks. Then we have 2 weeks of chronic DBS or sham control treatment. 3 weeks later, we evaluate the effect of fair conditioning, in vivo ALTP, and the circuit inhibition. Of course, we have 4 groups. Use the DBS parameter, which is typically used in the clinic. This experiment were performed in the female heterozygous mice because it's of their clinical relevance. Some found that DBS in the wild type mice do not, make a change, but in the mutant mice, compared to sham treated, DBS increased fair memory. As a result, it's rescued to the wild type sham level. Unexpected, we also showed that acute fair memory is increased as well. So this data shows that 40-cell DBS rescued the hippocampal memory in the female mutant mice. So also checked the DBS effects on LTP. We have 4 groups: wild-type sham, wild-type DBS, hate sham, hate DBS. This is a hate sham group. Compared to wild-type sham, there is a clearly impairment for 3 days. But DBS bring up the LTP back to the wild-type level completely. So the last piece of data we show is that feed-forward inhibition. This is a summary of the FDI index. DBS do not make a change in the wild-type mice, but bring up the FDI index to the wild-type level. That means 40-cell DBS actually reduced the feed-forward inhibition and normalized to the wild-type level. So in summary, I have shown you that MAP cells mediated the perforant path to the dentate granule cells, the feed-forward inhibition. In wild-type mice, the perforant path has a stronger excitatory input to the MAP cells than to the dentate granule cells. Under this condition, the inhibition and the excitation is balanced, and the mice shows normal memory. After CDKL5 loss, perforant paths have even stronger input to the MAP cell and even weaker input to the dentate granule cells. So the feed-forward inhibition mediated by MAP cell to the dentate granule cell is increased. Under that condition, the EA balance shifted to the inhibition. The mice lose the hippocampus-dependent memory. DBS in the phonics could rescue the EI balance and LTP, then bring the hippocampal memory back. So the work I presented mostly performed by Song Hao. She already moved to her own lab. Qi Wang performed the slice work, and the Lolo Foundation and my NIH grant support this project. Thank you. Now I will take your questions.